Physics of the megaloop. We're going to go step by step here. First off, we have the black arrows, and those represent the lifting force that the rider is subjected to. Because lines can only transfer forces in tension, the force will always be parallel to the lines. So we have an almost vertical, not almost vertical, let's say 30 degrees. Right at launch, the kite is pulling mostly up, and it's experiencing apparent wind of wind speed plus whatever small upward motion it may have. And this is going to be enough to get the rider jumping and ready for the megaloop. Now we see the kite starting its turn, its loop. It's almost pivoting here. So the apparent wind is going to be not much more than it was at launch. As the kite starts to loop, it accelerates and its speed through the air increases significantly. It's curving around. So the aerodynamic forces are combining. We have an apparent wind of the kite's arc through the air. Added to that, the wind speed starting to hit the canopy square on. These are going to combine and create a significant amount of line tension and forces to pull the rider. And notice this black arrow is starting to slant down more. We're changing the direction of this force. So we have the force about 45 degrees now. It's going to be a little more horizontal pull than vertical pull. So this force vector, the black line, is the force the kite is exerting on the rider. And we can break that down into a vertical and horizontal component. The vertical will counteract gravity, and the horizontal will only be affected by the inertia of the rider. So once that rider gets accelerated horizontally, he's going to keep going unless we do something about it. More on that in a little bit. Here we have the maximum force, and notice how almost horizontal this force vector is. This is going to be a very strong pull, almost completely horizontal, and this is why we see such an increase in horizontal motion between these two slides. Again, we have the kite's circular rotation through the air, creating its own apparent wind over the airfoil, and we have the 25 knots of wind hitting the canopy square on, adding to this pulling force. However, this won't last forever. As the entire system is accelerated up to close to wind speed, the aerodynamics will break down. Here I've calculated this about 24 miles an hour horizontal, an average of 1.2 g acceleration between when the rider was basically stopped at launch and here where he's laid out like a Superman. Now, here's where the pendulum begins. At this stage, we've extracted almost all of the energy we can out of the wind. The entire system is traveling with the wind, so the wind speed basically has no effect on the canopy. What's more is the loop is finished, and the kite is not traveling through the air very fast anymore. So now we need to recover from the situation, and this is where the pendulum comes in. What the rider does is sheets out, letting the kite fly back upwind. Now this does a few things. First, it basically kills almost all the lift generated, and that's why you can see the black arrow is shortened. Okay, the tension is less. There's less force on the rider. There's still a little bit of vertical and a little bit horizontal, but not that much. The rider's virtually swinging and falling in the direction of the red arrow, and the kite is going the opposite direction. So this is not a true pendulum because the top of the pendulum is moving in tandem with the rider. So back at this slide, you can see this is where slacking of the lines can occur because the kite is not able to pull anymore. The force diminishes and you might get slack in your lines where you actually get a true free fall until you get to here where you fall below it and you regain your tension. So now that the kite is back over the rider, it is flying upwind. The apparent wind over this wing, this kite in this scenario, is more than wind speed because it's wind speed plus the velocity, the ground velocity of the kite. So that would be somewhere around 35 something miles an hour. It's very easy to get some nice pulling force from a kite that's flying upwind in this manner. So the kite is flying upwind, the rider is still swinging downwind, and this is where he's going to sheet in and pull some of that speed back into lift. You can see the black arrow is increased again. That's line tension building. It's slowing his fall. Ideally, he's going to be coming down pretty slow now, maybe even getting a second bump, and just traveling pretty quickly in the direction of that red arrow. Now, if he's smart, he's going to let the kite fly behind him, and then we're going to get these force vectors split again. We still have a very large vertical component. We need to constantly fight gravity, otherwise we're going to fall. But we also have a small vertical component, a horizontal component, and that's going to slow the rider because he is going extremely quickly right now. If he lands, he can easily crash. This will slow him down, make him a better landing. And the kite is looping back around downwind to get back into a powered state. Let's see that whole thing again. Here we go, slide by slide. Boom, 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 boom. The loop begins. Notice that speed. The kite is looping, is traveling extremely quickly compared to here. It's moving, but not that much, not that fast per frame here. And then once we get to here, this is one frame's movement. And it is really yanking right here. Now notice that the loop basically stops. And here's where you can stall it if you want to stall it to get the timing of that recovery swing better. Again, traveling upwind here, easy to get apparent wind. With the wind already blowing from the right to the left, add that to the ground speed of the kite. Badooshk. Alright, stop it.